Okay, so we have motivated how it's it may be possible to represent a periodic function as as a series of as a sum of a bunch of sines and cosines, right? So, and specifically we looked at the example of the harmonics and overtones of a musical note, right? So that's the problem of Fourier series. But before we go there, we will before we describe like a prescription for how to get the Fourier series for a periodic function, let's look at the idea of the average of a function, right, which is the subject of for this lecture. Okay, so the average of a function is something that we can understand intuitively based on how we look at average of given a bunch of numbers. We would just add them up and take the and divide them by the number of these numbers that you're working with. And likewise, if you're given a function on some interval, right, you just integrate, which is like a sum itself, right, where there is a limiting procedure that we are considering, and then you divide by the length of the interval, right? So this is the notion of the average of a function f of x on an interval. Now, the average of a function appears in many contexts, right? So let's look at a few examples. So the average of sine of x over any number of periods is going to be 0, right? As long as you take a full period. If you take an average over half a period, then it's not going to be 0, right? So the average value of the velocity of a simple harmonic oscillator over any number of vibrations is 0, right? Because it's really the idea of averaging over a sinusoidal function is going to give you 0. But many times, more information may be contained in the average of the square of this function, right? So, if a function is spending equal amount of time, above the x-axis as it spends, or the time axis, above the time axis as it spends below the time axis, then although on average the function itself may be 0, it's still the square of this function may also contain information, right? So many times it's useful to consider the average of the square of your function, right? For example, when you're looking at alternating electric current, right? So we know that it's a periodic function, and the square root of the average of the sine squared, it's known as the root mean square or effective value of the current, right? If you just blindly do an average of this current function, you would just get 0, right? But clearly the current being 0 is not an accurate way of representing what it's doing, right? So it's definitely has the current has can do things for you, right? Which means that it's not just a 0 object. So here a more useful quantity to to measure the current is in fact the root mean square or effective value of the current, and which is what you would measure if you took an AC ammeter, right? So in the example of the simple harmonic oscillator, so the average kinetic energy is something that you might be interested in measuring, right? So that would be given by half m average of v squared, right? So when you're looking at the kinetic theory of gases, you have lots of particles, and there too you're interested in measuring the average of v squared is of great importance, right? So you might have seen these concepts of equipartition theorem in statistical mechanics. These kinds of averages are of importance, right? Sometimes one is interested in the time average, sometimes one is interested in some ensemble average, and so on, right? So all kinds of averages are of interest, right? So for our discussion, we are looking at the properties of just a one-dimensional function, right? And so the average is taken on certain intervals here, right? So you can the most basic thing that you can do given an entire function and you want to bring it down to just one number is to just take its average, right? It's like a crude representation of the information contained in the entire function is just this one number. So for the purpose of this discussion, let's say that you're looking at the average of sine squared nx and cosine squared of nx in the interval minus pi to plus pi. So let me fix the interval to be minus pi to pi now, and then you'll see in a moment we can actually shift this this period about, right? We have much more freedom. So if I do this, so then I will see that in fact, since this quantity is equal to this quantity, I can just add the 2 and then divide by 2. So it's half of 1 over 2 pi integral minus pi to plus pi sine squared of nx plus cosine squared of nx dx. Therefore, but this quantity is nothing but 1, right? So therefore, I'm going to get just a half. So the average value of sine squared of nx, right, is half, right? As long as you have taken the average over a multiple of the period of this function, right? Okay, so let me give you a more general argument. So if you have a function which has some period p, right? So the average value of f is the same over any interval of length p, right? So I have looked at, I have taken it from minus pi to be safe in this argument, right? But all you need to do is find the period of this function, whichever function it is, right? If you have an f of x, an arbitrary function of periodic function with period p, so the average value of this function f is the same no matter which interval of length p you consider, right? So the argument is the following. So let us consider the average of this function over a period of length p starting at some arbitrary point. So I am interested in this integral a to a plus p f of x dx, and then I have to divide by the length of the interval, which is going to be p, right? So I of a, so you would think that this is, a priori you might expect this to be dependent on a, but let's look at what happens if I compute this at some other point a plus delta a, right? So this delta a does not have to be infinitesimal. I'm not even thinking of that at this point, right? I'm just considering some other point which is at a distance delta a away from a. So I of a plus delta a minus I of a is, I'm just in place of a, I have to put a plus delta a. So I have a plus delta a here, I have a plus delta a plus p f of x dx minus this original integral. So then I notice that there is this interval which is common to both of these integrals, and that is basically it runs from a plus delta a all the way up to a plus p, right? So there is a leftover bit which is from a plus p to a plus p plus delta a, so that I have to keep, and then I have to also subtract this other part which is also left out, which is a to a plus delta a, so that part is also left out, right? So from here you see this, and therefore I have these two small components or big component, doesn't matter, it's something that we cannot say because delta a is arbitrary, right? So but it's precisely this component and this component remains. But now we can argue that in fact these two are exactly the same, right? These two will cancel and you'll get 0, and the reason is you can just do a change of variable. X can be made to go to x plus p, and then you'll immediately see that if you invoke the periodicity of this function f of x plus p is equal to f of x, therefore both these integrals are the same and the denominator is the same p in both, therefore the difference of this will be 0. Therefore we have managed to show that I of a plus delta a is equal to I of a. So therefore I of a is actually independent of a. You could have started at any point as long as you cover a length p, which is the period of this function, you're going to get the same average value, right? So we will see in our discussion which will work out the Fourier series representation for an arbitrary periodic function. In fact, the average of this function is like one of the basic ingredients which goes into this Fourier series, and then there are more complicated, there are other elements which will come up, right, in our discussion. But this lecture is simply a warm-up exercise once again, but we have taken one more step towards working out the Fourier series of a periodic function, which is coming ahead. That's all for this lecture. Thank you.